Hey everyone. So in the last video I went step by step through the derivation of the OLS estimator for both the intercept and the slope coefficient in the bivariate case, right? And we ended up with two different formulas that you've already seen in the textbook, but that wasn't, directly derived from the sum of squared residuals going through all the math. But now we actually went through it step by step, and now you can confirm for yourself that the beta coefficient, or the OLS estimator for beta, can be written as the sum of xn minus x bar times yn minus y bar divided by xn minus x bar squared. And once we have our parameter estimate for beta hat, so beta hat, we can plug in y bar and x bar as well as beta hat to get our estimate for the intercept. Okay, so the goal of this short video is to show that we can directly, very easily program this in R as a function, and then confirm that the result that we get from using the lm command is equivalent to our derivation. Okay. So programming this estimator that we derived as a function in R is relatively straightforward. We call this function now OLS2var, so this only works for the bivariate case. And this is a function that takes two arguments. We have our y, that's our outcome variable, and x, that's our independent variable. Okay, so we just need those two variables. The input here would be a vector for both, a numeric vector for both. Okay, and then all we have to do is basically translate the functions that we derived here for beta hat and y hat into R. Okay, so translating this into our code is just x minus mean of x times y minus mean of y. That's the part up here. And then we're summing this across all individual observations. And since all observations in x, those are just in x and y, that's just the vector each, right? So we can use the sum command to sum up all the elements of that vector. And then we divide this by the sum of the squared sum of the squared deviation between the individual x's and x bar, right? So that's basically just the variance. X minus mean of x squared. All right, so that is our beta coefficient, and then we have our alpha, our intercept, where we now just have to take our mean of y minus the beta that we just computed times the mean of x, and that is our alpha hat. So the output will just be two elements, alpha and beta, and we're just returning this right here. So that's it. That's already an OLS a function that estimates OLS in the bivariate case. So let's check if this actually works and if this is consistent with the LM function that we worked with previously. So let's go back to our social pressure experiment that we worked with both in the lecture videos as well as in the assignment. In the lecture videos, which specifically in one of the previous videos I worked with the subsetted data set that only focuses on people who received the neighborhood message, so the social pressure message, versus the control group. So we're reading in our social.csv, that's the data file that we've been using in the past weeks as well, and we're subsetting by only including the control condition and the neighbor's treatment condition. Okay. Then we already talked a bunch about different types of models that we could estimate here, and one of the models would be just this bivariate comparison between the treatment group and the control group, and we see here primary 2008, so that's turnout in the 2008 election, and our treatment, dichotomous treatment indicator in this case as an independent variable. And then we see an intercept of 0.29. So people in the control group in expectation had a turnout rate of 29 or 29.7%. And we saw that in the treatment condition, so people who received this social pressure treatment, the turnout rate was increased by 8.1 percentage points on average. Okay, so that's the result that we receive using the LM command that we used before. And now we can do exactly the same using our OLS2 var, also a bivariate OLS function. The input here looks a little bit different, of course. We didn't specify this function argument or a data argument. All we'd take as an input is our dependent variable first, which is just primary 2008, and our independent variable. And here what I'm just doing is remember that this is basically a character variable that has two outcomes, right, or two categories right now, control and neighbors. And I'm just turning this into a logical statement. So this is equal to true if the treatment condition is neighbors, and it's false in any other case. So that's just the control group. And so this will be interpreted as kind of dichotomous 1-0 variable, right? So we talked about interpreting dummy indicators in the regression context as well. But the important thing is, if we run this, and the code is of course on RStudio Cloud as well, so you can play around with this as well, is that the coefficients are the same. We have the same intercept alpha of 0.296 or 297 and beta for 0.0813. Okay, so using our custom OLS custom bivariate OLS function, we get the same result. The expected turnout rate in the control group was about 30%, and in the treatment group the expected turnout rate was about 8 percentage points higher than in the control group. Okay, so this confirms that both our derivation was accurate, and that the formula gives you the same result as the pre-packaged LM function, which is always reassuring. In the next video, I'm gonna go a little bit more through the math of the bivariate OLS estimator, and show you one important property, which is that the OLS estimator is unbiased.